Hello everyone, I'm Omid Mohaddesi, and in this presentation I will talk about our paper To Trust or to Stockpile, Modeling Human Simulation Interaction in Supply Chain Shortages on behalf of our research team at Northeastern University. Simulation games are used as a research environment to study human decisions. Methods such as gaming simulation and participatory simulation, game-based simulation environments such as gamettes have shown great promise in studying human behavior. Researchers usually use these environments to validate and improve the underlying simulations by observing or modeling human behavior. However, a key challenge in modeling human behavior in these environments is the system's dynamic nature. As a result, there is a trade-off where the state of the system affects humans' behavior, and this state can change due to human interaction with the simulation. We also usually use these environments to generate and test hypotheses, and in doing that, we create manipulations that may have some unexpected effects on human behavior. So, when we combine these manipulations with a dynamic system, teasing out their effect becomes more complicated. Our goal is to extend existing research in behavioral modeling within game-based simulation environments by characterizing the human simulation interaction. We do this in 3 steps. First, by characterizing the simulation, then characterizing the behavior, and finally by characterizing the interaction while taking experimental manipulations into account. To achieve this goal, we use a gamette environment as described in our previous work to put human participants into the loop of a simulation that replicates a supply chain environment. We considered a supply chain where players play the role of a wholesaler and need to order from a manufacturer and allocate their inventory to downstream health centers, with a goal to minimize cost and maximize profit. In addition, at some point in the game, a disruption happens that limits their supply. After a tutorial, players will start making decisions on week 21 of the simulation and continue playing for 35 game weeks. On week 28, players are notified about the disruption. Moving forward, we had 2 hypotheses. First, we hypothesized that if we provide order suggestions to players, they deviate more from these suggestions when facing a disruption compared to a normal condition. In addition, we hypothesized that if we share supply chain information with players, it will reduce their deviations from those suggestions. To test the second hypothesis, we considered a manipulation where, for some players, we provided information on their supplier inventory. We asked 121 online users to play the game and randomly assigned each one to either an information sharing or no information sharing condition. For characterizing the system, we used principal components analysis to reduce the dimensionality of the simulation. Here we considered the state of the system for player's role, which is the wholesaler. So we considered inventory, demand, backlog, received shipments, and on order. We found that 2 principal components explain 77% of the variance in the data for these supply chain variables. Here you see the scores from these 2 principal components. Each point here represents the state of the system for each player and in a certain week. By performing hierarchical clustering, we found 3 system states. These states represent situations where the system is either stable, or it is in a supply disruption state where players are unable to satisfy their demand, or it is recovering from disruption and players receive large shipments after a shortage period. By considering the states that most players experience every week, we divided the gameplay into 5 phases. We will use these 5 phases to characterize the interaction of players with the simulation. To characterize the behavior, we used a hidden Markov model, or HMM in short. An HMM describes a Markov process where a set of observed outputs can be explained by a set of hidden states. What we are trying to do here is to infer the set of hidden states. We consider our observed outputs for the HMM to be the player's deviations from order suggestions, and we try to find response modes that explain the amount of deviation. Using HMM, we found 2 modes of negative adjustment, a control mode, and 5 modes of positive adjustment, where in each response mode, players show different levels of deviation from order suggestions. On the left, you see a snapshot of ordering scene that shows order suggestion, and the plot on the right shows the inferred response modes from the HMM and how each one corresponds to a specific range of deviation. Now imagine that each player can have a different response mode at each time point during the game. So we can consider the sequences of players response modes and compared these sequences across all players. By doing this, we found 3 types of players who were showing different patterns in their decision making. We called them hoarders, reactors, and followers. Hoarders tend to stockpile more frequently and are more frequently in positive adjustment modes. Reactors follow order suggestions before the disruption, but react to the news about the disruption and transit to other response modes. And finally, followers almost always follow the order suggestion. Now that we have characterized both the system and the behavioral responses from players, we can look at the behavior over the system phases that we described earlier. We can do this by counting the frequencies of response modes across hoarders, reactors, and followers, and over the phases of the system, and separately for players who received information sharing and those who didn't. We can see that hoarders and reactors deviate more from order suggestions when facing the disruption, especially in phase 2 and during the shortage in phase 3. This supports our first hypothesis. And while hoarders tend to stockpile more than other players, those who received information sharing deviated less by being in mode of P1 more frequently. This shows that information sharing reduces order deviations, which supports our second hypothesis. An interesting but unexpected finding here is that information sharing leads hoarders to hoard even more after the shortage period is over. Most simulations have a high-dimensional space and can generate different dynamics, especially when they are a model of a complex system, such as a supply chain. Games are complex systems too and can generate different experiences that result in different behaviors. Including manipulations may also result in unexpected interactions. These are all reasons that make game-based simulations complex environments for behavioral modeling. Through characterization of the system, the behavior, and the interaction, we try to shift the focus to human simulation interaction as a research area within HCI and show how these characterizations help for making sense of human behavior in such complex environments. Future research can extend our approach by extending the system and behavior characterizations. For characterizing the system, we can differentiate between dynamics that are driven by the simulation or are the results of human behavior. For characterizing the behavior, we analyzed observable response by considering in-game decisions. But future research can study non-observable responses, such as mental models or belief updates. And with that, we would like to thank the anonymous reviewers for their comments and Chi22 organizers for the opportunity to present this work. Please check out our website for more information and feel free to reach out via email or Twitter if you have any questions. Thanks for listening.